Let's continue from where we left off yesterday. We were discussing about the data flow graph as a way of representing signal processing algorithms, and we were essentially trying to understand what it means to talk about the concept of an iteration of a data flow graph. And the goal that we are sort of heading towards is essentially we want to be able to understand what does it mean to define something called the iteration period. What is the minimum possible iteration period that can be usefully used on a graph, and how does that help us in turn with actually implementing the data flow graph on some kind of hardware. Okay. So the example that we were working with yesterday was an IIR filter with the equation y of n equals a times y of n minus 1 plus x of n. What we saw was that the data flow graph, one possible representation of the data flow graph for this could look something like this. There is a source that emits x samples. There is an adder. The output of the adder is essentially the y of n. One sample delayed version of that adder goes through a multiplier with the coefficient a and comes back in here to the adder. Okay. So structurally you can see that it looks slightly different from what I drew yesterday, but that's just a question of how I have rearranged the nodes in the graph. So obviously that doesn't make any difference, but more importantly, keep in mind that the data flow graph representation itself may not be unique, right? Depending on who is drawing it and what you consider as the main computational components in your system, you could end up with slightly different looking versions of the graph, although more or less you expect it to look more, substantially similar, right? So for example, there might be some other version of this graph where I might not explicitly draw the source node at all. I might not consider that as a separate unit. Okay. So those are sort of minor changes that we will ignore. And what we are going to assume is that for the most part, if you are given an equation, then it's possible to come up with a data flow graph representation of that corresponding equation. Okay. We also talked about the notion of actors. Essentially each of these nodes over here is an actor, and the notion of firing of these actors, right? What we mean by firing is one execution of each of the functional nodes, right? And what we said is based on this we can come up with a so-called trace. An example trace would look like this: S0, okay, I need to relabel these. I'll call this A for adder and M for multiplier. So that one possible trace through this is basically S0, M0, A0, S1, M1, A1, S2, M2, A2, etc. Right? Keep in mind that this is only one possibility. As we saw, there are many different possibilities that can come up over here. What we would like to understand is, are there any fundamental properties, any limitations on the kind of different traces that we have, and in turn can we get some useful information from understanding those traces. Okay. Now again, the way that I have written the trace over here makes it explicit that first S0 happens, then M0, then A0, then S1, M1, A1, etc. right? That is how it would look, for example, if you were writing a C code to implement this entire system, right? Because C is fundamentally a sequential programming language. C, assembly, Java, any of those are fundamentally at their core sequential programming languages. The assumption is that when you write a function, each step in the function is executed one after the other in that correct sequence in which it has been represented, and the final output is then obtained after all the steps have been executed. Okay. That's not really necessary. I mean, the data flow graph by itself is not imposing such a restriction. So what we will see next is it possible to sort of get around that? Can you sort of change the way in which those are executed, and how can we figure out that what are the true dependencies, that is something that has to happen after something else, versus just something which happened because of the way that I wrote the trace. Okay. Now I am going to make a further assumption. that each of these nodes has a certain execution time associated with it. And I will call them respectively TS, TA and TM. So it's obvious to you which refers to which, right? TS is the time for execution of the source. That can be thought of as maybe the time required for the source. Maybe it's an A to D converter. How much time does it take to convert one sample and provide it to you? Or if you are reading from a disk, it might be the time required for reading one sample of data from the disk and providing it, the average time perhaps, okay? TA is the time required to perform one addition and TM is the time required for one multiplication, okay? For now, assume that all are equal to 1, right? That's just so that my drawing becomes a little bit easier. It has no real impact on the analysis that we will be going through later, okay? Right, so with this in mind, let's now look at, can we define something called the iteration period and find out how much time it takes on average to perform one iteration of this graph, and from there can we go further and find out are there any fundamental limits on this iteration period, okay? So with the numbers that I have put down over here, what's the iteration period for this trace that I have written? 3, right? Why? Because essentially what I can look at is this is one iteration, right? S0, M0, A0. Once I have finished all 3 of them, essentially it means that all 3 actors in the graph have executed once. That is the completion of one iteration, okay? So this I will call as iteration 0, okay, because they correspond to S0, M0, A0. This one I will call as iteration 1. This is iteration 2, etc., right? So the iteration period is equal to 3 for the above trace, okay? Now let's look at a slightly different trace for the same graph, okay? What I am going to say is S0, S1, M0, A0, M1, A1, S2, S3, M2, A2, M3, A3, right? This is also a valid trace, right? Now I am just putting dots at the end. Either you can assume that it's going to be a periodic repetition of the pattern that we have seen so far, or something else. I don't really care. All that I care about is what I can see so far and what can I sort of deduce from the trace that I am able to see up to this point. If it is a periodic pattern or beyond that, then yes, I can extrapolate from what I am seeing over here, but otherwise I can only calculate whatever I can see from the trace, okay? Now is this a valid trace? That's the first question, and the reason I have said it is a valid trace is because none of the dependencies have been violated, right? We already saw from this yesterday that S can execute as many times as possible as it wants to right at the beginning, because it does not have any dependencies. It's like an A to D converter. As long as the input data is present, it will keep on generating outputs. It's not waiting for anything else, okay? If the next stage can't store the data or can't take the data and do something with it, that's not the ADC's problem, okay? It will just generate data as and when it is ready. But the adder and the multiplier have cross connections, okay? So there is a bit more of a restriction in terms of what we can do over there, which is why after M0 I can't really have M1, right? Because M1 depends on the output of A0 and A0 of course depends on the output of M0. Therefore this sequence M0, A0, M1, A1 is fine. But after M1, A1 I can't go to M2 because, or rather I can go to M2 if necessary, right? But I can't go to A2 for example until S2 has happened. which is why I have written this particular sequence S2, S3 and so on. Okay. So now that we are convinced that this is a valid trace, let's sort of see how do we define iteration period over here. Okay. First of all, what is iteration 0? Okay. What would you consider as iteration 0? All the operations in iteration 0 have to get completed, which basically means that up to this point. Right? These three are completed. At that point, iteration 0 has completed. What about iteration 1? It basically corresponds to S1, M1 and A1. Okay. Iteration 2 corresponds to these three. Iteration 3 to these three, etc. Okay. So, a couple of observations here. One is iterations can overlap. Before the 0th iteration has completed, the second iteration has started. Okay. Is it possible for the second iteration to complete before the 0th iteration? That does not really make sense, because by definition the first execution of M or A or whatever it is considered as part of the 0th iteration, right. So, all the executions, the first round of executions will all be associated with the 0th iteration, the second round of executions will be associated with the first iteration and so on. Okay. So, it does not seem possible for iteration 1 to finish before iteration 0, but it can start before iteration 0 has finished, that much is clear. Okay. The second thing is, what is the iteration period that we have over here? That is a slightly more tricky question, right, because we have two factors operating at hand, operating over here, right. One is the fact that how much time did it take for iteration 0 to complete? It took 4 time steps. It started at time 0, and went on up to time 3. Right, went on from 0 to 3, so 4 time units. Iteration 1 goes on from 1 to 5, right, which is 5 time units. Iteration 2 goes from 6 to 9, 4 time units. Iteration 3 goes from 7 to 11, 5 time units and so on. Okay. But what is this? Is this really the periodicity, or is it just the time required for finishing that iteration? It is the time required for finishing that particular iteration, right. So, this number that we are seeing over here is not really the iteration period, because iteration period is sort of a property of the long term trace, how on average how quickly are iterations getting completed. That word on average is, the phrase on average is a bit tricky. That is strictly speaking not the exact definition of iteration period, but for the time being, just for ease of understanding, I am going to use that. Okay. So, in any case, one thing that you can see over here is the time required for one iteration to complete, first of all, can vary between 4 and 5 over here, right, but that is not really indicative of the periodicity either, of how, at what rate we are finishing iterations. Okay. This number, this time required for finishing a particular operation, this is referred to as the latency. Okay. The latency essentially means what is the time required for from the start to finish of a particular iteration. Okay. You can think of it as from the time that I give the inputs, how much time does it take until the last output is received. Okay. So the latency in this case could be 4 or 5 time units. The worst case latency is 5 time units over here. Okay, at least for whatever I have shown so far, assuming that the same pattern continues periodically, it remains that way. The minimum latency is 4 time units, the maximum latency is 5 time units. So that's okay, right? What about the iteration period? How do we find that out? Right? Another word for the iteration period, in fact, in this case, is something that we will call, again, so there are two things at work over here. One is what is the average iteration period. The other is something else called the initiation interval or the iteration interval. Okay. So average iteration period is sort of easy to understand over here. Time required for finishing n iterations divided by n. Okay. So in this case, let us take time for 4 iterations divided by 4 is equal to how much? I am able to finish 4 iterations starting from time 0 and finishing at time 11, therefore 12 time units. Okay. So 12 time units divided by 4 and this comes out to be 3. Okay. So even though any given iteration is taking more than 3 time units, okay, I am intentionally using the word time units to sort of keep it neutral. If you find that difficult, then just think of it as clock cycles, right? And you can basically think of each of my operational units, the S, A and M, as maybe taking 1 clock cycle to perform their work. So every tick of the clock, they do something, right? But the reason I am just saying time units over here is because it need not be clock cycles. It could be even some kind of an asynchronous system where each one has its own free running clock internally and takes a certain amount of time, or each of those could even be a combinational system where the time unit is actually nanoseconds, right? The same analysis holds in all cases. Okay. So average iteration period works out to be 3 time units, even though the latency can be higher than that. Okay. The next question essentially comes out to be the initiation interval, okay, or the iteration interval. What do I mean by this? I am essentially asking the question, after iteration 0 starts, what is the time before iteration 1 can start? Okay. So from I0 to I1, what is the time? 1 clock cycle, 1 time unit, right? But what about I1 to I2? I1 started at 1, I2 starts at 6, okay. So this is 5 time units, right? So what we see over here is an interesting thing. One is the iteration interval, the initiation interval, right? It had a minimum value of 1, that is I started I0 on 1 clock cycle, and in the very next clock cycle I started I2, or rather I started I0 and then I started I1, okay, on the next clock cycle. Therefore within 1 clock cycle time difference, I am able to start my next iteration, not complete it but start it, okay, that is my initiation interval. But was I able to again start on the very next clock cycle after that? No. Once again I had the problem that I then had to wait until I0 and I1 completed before I2 could start, okay. So I2 essentially goes to 5, 5 time units later, okay. So in all of this, what we are ultimately trying to find out is, are there any fundamental limits? Okay, so all of this was based on just traces that we took through the data flow graph, right? Now we are going to try and relax one assumption, which is that everything is going to happen in a sequential trace, and we will see how the structure of the traces changes and what impact it has on the latency and the iteration period. Okay. So, these values, the latency and the initiation interval, right, in particular are very important parameters that we will have to keep in mind later as we go for actual synthesis of circuits. Okay. The reason why the initiation interval can sometimes be more important than the latency is because of something called pipelining, which basically allows us to have multiple things running at the same time. Even if each individual computation is taking a long time to finish, I am still able to get a high throughput because after some huge initial latency I start getting outputs very quickly.